So the example is from your slides. We want to find AV, R in, and R out. Okay? This is the circuit. Okay. Now the assumptions are that VBE is 0.7 volts, beta is 100, or 200, sorry, and VCE sat is 0.2 volts. We don't really have to worry about this because the device should be in active region if you're going to use it as an amplifier. But it's a device parameter that is given. VCC is 10 volts, RB1 is 70 kilo ohms, RB2 is 30 kilo ohms, RC is 4 kilo ohms, RE1 is this guy up here, RE2 is the guy down there, is 500 ohms, RE2 is 1 kilo ohms, RL is 20 kilo ohms, and RS is 10 kilo ohms. Okay, so it looks like a jump from what we analyzed so far, right? So far we looked at the circuit with just one resistor at the collector and then maybe one resistor at the emitter side and analyzed that. But this is how a real circuit will look like, right? So you need to have biasing there. You have these coupling and bypass capacitors. Your source may have an output resistance. All those things will be included in real life. So once you see that, you can always go back to the small signal model for the transistor and solve the circuit at DC and then use the small signal circuit to figure out all the parameters that you need. However, if you know your circuit theory, if you know your stages well, you can use the analysis that we have already performed in order to solve the circuit. And I'm going to show you that. But I highly encourage you to do the small signal analysis in a proper way after you do the DC analysis. And just convince yourself that the results will be the same. Now, so for this circuit, the first thing we need to do is to do the DC analysis. You notice that there are three capacitors here. CC, these are the coupling capacitors, and we talked about the role that they have, that they separate stages at DC from each other. So they let you focus on the DC analysis of one stage at a time. But you also have this CB device here, CB capacitor here. And when you're analyzing these circuits, we assume all of them are short-circuited at AC frequencies, okay? So in this case, what happens is that if you replace CB with a short circuit in your small signal model, it's going to short-circuit RE2. And what you're doing here is that in the emitter circuit, you have a combination of RE1 and RE2 that gives you the bias stability that you needed. But for AC performance, we noticed that RE2 drops my gain quite a bit. So I may not really want to sacrifice that much gain. What I can do is that I can keep both of them for DC, but for AC, I put a portion of that resistor that I don't want to be there in parallel with the capacitor. And then by having a capacitor there at AC frequencies, at high frequencies, the capacitor will be a short circuit. It will basically take out RE2 out of your AC circuit, and effectively you're dealing with two resistors for DC and AC analysis. For DC it is RE1 plus RE2. For AC you only have RE1 left, and its bottom side is grounded. So that's called the bypass capacitor. I'm bypassing RE2 for my AC behavior, but I need RE2 for the DC stability issues that we mentioned before. So we need to solve the circuit first. What you need to do is to go and do the DC analysis. So for DC analysis, I draw the DC circuit only. I have RB1 and RB2 here. So the goal here is to establish or to figure out what are the values of, let's say, the collector terminals, the device terminals and the currents, right? IC is the most important one because we needed IC to figure out GM and RPI and all that. So to solve the circuit, and then what has happened is that CC1 and CC2 has separated the load and the source from my circuit. CB is at DC an open circuit, so I don't have to draw it. This is what I have. This is the circuit that I need to analyze. And at this point, I'm hoping that you have enough experience with DC analysis of the BJT circuits to quickly solve this. And one approach is to figure out the Thevenin equivalent circuit of this portion of the circuit, the combination of RB1 and RB2, and figure out IB from there. I'm not going to go into much detail here because I'm sure you have enough experience here to solve it. Okay, so if you write your KVL from the base to the emitter to ground, this is the result, this is your IB, and then from here you can find IC. Okay, in terms of numerical values, the answers are going to be, once you plug in the values, the collector current is going to be 1.4 milliamps, and the collector voltage is going to be 4.3 volts, and the base voltage is about almost 3 volts. So you can show that the BC is off. Right? You verify the assumption. And at this point, and then VE, you can actually do the calculation there as well. VE is about 2.1 volt too, right? So you can verify that the device is, if this is going to be actually about 2.8 volts or 2.8. Anyway, the DC analysis, I'm assuming at this stage you are comfortable with, right? That's the result, and if you want, you can just solve it to have a little bit more practice. What we are focusing here is AC analysis. Now, I go back to that circuit, and I notice something, that at the core here, I have a signal that is produced by Vs and goes and propagates through this circuit. I have a signal that is going into the base, so let's just call this Vi. And it excites my transistor, and the transistor does something, and then something happens in the collector, but this is where my output is taken from, right? So the input has gone to the base, The output has come out of the collector. Now the other thing I notice is that there's no other connection between the base and collector or the base and emitter, right? So it's just purely, if I look at VI and VL, if I do not include the circuits behind and after them, between VI and VO, I have that common emitter stage with emitter degeneration. In that case, just RE1, right? So I can use the analysis that I have done before to solve this circuit. How? We're going to see in a second. So I realized that there is no connection between base and emitter, base and collector beyond that transistor itself. Sometimes you may have a resistor between base and emitter or a resistor between base and collector. In this case, we don't. So this is the basic stage that we analyzed here, right? Between the base and collector, we only have one RC and one RE, and that's it. So I'm going to use the analysis that I have, or the data, the calculations that I did here, to make my life a little bit easier here. For you, I strongly suggest doing a full small signal analysis on this circuit first, then comparing the results with the AC analysis that I'm going to show you in a second. So now I'm going to draw the AC circuit. It is not the small signal circuit, it is the AC circuit, meaning that I'm going to get rid of the DC sources in my circuit, and I'm going to short circuit all the capacitors that are used for coupling or bypass purposes. So from here, I can go and show that the AC circuit looks like this. So remember, this is not small signal, this is AC. This is how I get rid of the DC sources and I get rid of the capacitors. So at the input I have RS and VS. Then the coupling capacitor at the input is short circuited. I have RB1 here and RB2 here. The RB1 at the top was connected to VCC, now I connected to ground. Then I have my transistor here, RE1 in the emitter circuit, and then RE2 is now bypassed by the capacitor, so it's replaced with the short circuit to ground. RC here goes to ground again at the top. The coupling capacitor at the output is now shorted as well. This is V out, and RL is here. Right? So I call this the AC circuit, right? I still have the transistor in there. I didn't draw the small signal. The only difference between this and the small signal model is that I'm using the transistor as itself. You can put the small signal model of the transistor there, and that will be your small signal. But my point here is that once you do the small signal analysis for a couple of those stages, we said there are just 3 basic stages, and you can identify the stage in your circuit, then you really don't have to do the full small signal analysis anymore. You can just go back and use whatever you've done for the analysis of that stage to and utilize that, right? But anyway, so what I have here is basically the amplifier here I have identified as a common emitter amplifier, right? So if you look at this, I have VO here, VI here, this is VI, this is VO. I know the output resistance when I look back here, I know the input resistance when I look into here, and then I've attached other stuff to it, okay? Now the goal is to utilize the information that I have before. So if I look at this part, I have some input resistance, I have some output resistance, and I have some voltage gain, okay, that I can go and calculate, and then attach that to the rest of the circuit. So the goal is to utilize what I know. So let me draw this a little bit larger, make it a bit larger. So this is my amplifier. This is the common emitter stage, right? I've identified it. Inside it, I have an input resistance, a controlled voltage source, and an output resistance. Okay? This is the amplifier. I put it inside the box here. Now, this amplifier is now connected to a load resistor at the output. And this is the V out that I'm seeing from the circuit side. At the input, what I have is RB1 and RB2. Well, look at that combination. RB1 and RB2 share one node in the middle, but the other end of both of them is connected to ground, so they're in parallel. So this is RB1 in parallel with RB2. And then I have RS and VS. This is VI to the input of my amplifier, right? It's not VS, it's whatever that is at the input of the amplifier. I want to solve this circuit, okay? But because I've done the analysis for the common emitter stage already with emitter degeneration, and I have the formulas for whatever that is inside that triangle, I can see that right away. My life is very, very easy now. Because what I know is from the analysis I did in the above, I know that Rin is equal to R pi times 1 plus GM RE. I know that AV is minus GM RC over 1 plus GM RE. And I know R out is RC, right? These three I know for an emitter, a common emitter stage with emitter degeneration. So I know everything inside that triangle. This is a linear circuit. I can very easily solve it. Now if I go back to the original drawing, I need to measure Rin or report Rin value and R out value for this amplifier as well, this new circuit. Rin that I need to report is measured from here. So let's just call it Ri instead of Rin because I'm already using, or maybe let's call this Ri, the guy inside here. So call this Ri and this Ro. So this is Rin that I need to report, and this is R out that I need to report. And the gain value is V out over Vs. Okay? So I need to figure those things out, but this is a linear circuit. This is just a bunch of resistors with one dependent voltage source. It's really making my life much easier if I look at that whole circuit like this. For example, if I want to start with calculation of Rin, well, formally I have to remove the independent source, so Rs and Vs go out. I attach my test source to the input of that circuit and I measure the current that goes in. But if I look at this circuit, when I look to the right of that arrow, to the right side of the arrow, all I have is one RB1 and RB2 in parallel and one Rin in parallel with them. So I can see that without actually even solving it, I can see that Rin is RB1 in parallel with RB2, the whole thing in parallel with Ri. Right? I hope this is clear, right? If I attach a test source, test voltage source to that node, remember Rs and Vs are gone. I measure a current through the combination of RB1 and RB2, and then a current through Ri of the amplifier. The sum of these two currents, when you divide the voltage by that, it's as if you have all these three resistors in series. So that's your Rin. What about R out? Again, I remove my voltage sources at the input. So the input is grounded. I'm looking back at the output here. I attach my test source to this node, right? And of course, RL is not part of that circuit anymore. Measuring Ry. But then in that case, if my input source is gone, then VI is 0. And therefore, the voltage gain that I have over the AVVI is 0. And therefore, what I see when I look back is just R out, RO of the amplifier, which I know is RC. So that also is easy. The only remaining bit that needs a little bit of calculation is the voltage gain now. So let's look at the voltage gain. I'll look at the output part of the circuit first. So I can see that V out in this circuit is a voltage divider between RL and RO times the gain of my amplifier, AVVI, value of my voltage source. So that one is AVVI. Okay? Now I don't know VI because I need to figure out V out as a function of Vs. I don't know VI yet. VI is unknown. So I need to figure out VI as a function of Vs. So what I can see here is that VI, the voltage here, if I want to find it as a function of Vs, again, I have these two resistors in parallel. That is one combined resistor. And a voltage divider between that resistor and that combination of resistors in RS. What is the combination of these resistors? This is just your Rin, right? So easily I can show that VI is Rin over Rin plus Rs times Vs. Well, look at that. I can eliminate VI from these two equations and have my V in V out relationship. So from this I can show that V out is RL over RL plus RO times AV times Rin over Rin plus Rs Vs. Okay, so this is for VI. I'm done. I can actually put in values in there and calculate the actual value of gain. Let's just go and put the value of gain that we know from before to make it a little bit cleaner. So V out over Vs is okay? So that's the voltage gain. Now, let's see what happened. With this circuit, by attaching a source resistance, by having a source resistance and attaching a load, two things happen. This is the gain of the basic stage, right? If my common emitter, the basic common emitter stage that I had before, right, with just emitter degeneration, that's the gain of that stage. Now, because I have a load resistance and I have a source resistance, I take a hit. The original gain that I had is now reduced. Why? Because only a portion of that voltage appears across RL. I have a little bit of voltage drop across the RO of the resistor, the amplifier. And at the input, same thing. The amplifier sees only a portion of the signal source. How much of it? Well, that is given by this expression here. So a portion of that signal from the source appears at the input of my amplifier. My amplifier amplifies whatever that it sees, right? It cannot amplify the portion of the signal that it cannot see or it doesn't know it exists. Only that portion of that signal appears across the input resistance. That's the portion that my amplifier sees. Then it does its duty. It amplifies that portion, right? So you get that gain, but at the output, you have a load resistance now. So again, there is going to be a voltage division between the load and output resistance of the amplifier. Now here right away actually tells you something else. That for this device, or for a voltage amplifier, why did we want to have a zero output resistance? Well, here is the reason. Because if the output resistance of your amplifier was 0, this fraction would have been 1, right? And then why do we want an infinite input resistance? Well, if it was infinite, if Rin was infinite, this fraction would have been 1, right? So you would have got the most out of your amplifier. All of that gain that it was trying to give you, you would have seen it. But now because of the input and output resistances of the amplifier itself, you see a fraction, right? The amplifier can only give you a part of that native gain that it could provide with, let's say, zero output resistance or zero input resistance. Of course, if your source is ideal and RS is 0, then you don't have to worry about the first part. All of that, RS 0 means this fraction is 1. And also, if your RL is infinite, if it is an open circuit instead of a load resistance, this output fraction is also 1. So we analyze the circuit with those conditions, assuming that RL is infinite and RS is 0. But then if you have that complexity, if you have that additional load, then you have to modify your equations as shown here. Now again, one more time, I would highly recommend you to do the small signal analysis, the full small signal analysis for this circuit, and show that you will have the same result.